begin by thanking the main organizers for giving me the opportunity to present this talk here. And I should say that I'm very pleased to be in this wonderful venue, my office being next door. So I'm going to talk about some analytic results from Conformal Bootstrap. And that's another thing that I should thank the main organizers for giving me this opportunity to masquerade as a bootstrapper. So hopefully that will be a word that will catch on soon enough. So since the seminal work of Ratajczak, Rychkov, Tony, and Vicky in 2008, as you heard from David's review talk yesterday, many interesting results have emerged using conformal bootstrap methods, enabling us to gain some insights about conformal field theories in dimensions higher than 2. And most of these impressive results, as was clear from the review talk, rely heavily on clever numerics. There are some sporadic results that are available which use analytic methods, and my talk will focus on some analytic results that follow from conformal bootstrap. And this talk is going to be based on some work that I did with my students Apratim Kaviraj and Kallol Sen, who are there in the audience, and it's based on these two papers and some work in progress. And I should at the onset say that this builds on work by Fitzpatrick, Kaplan, Poland, Simmons-Duffin, and a simultaneous work by Komargorsky and Zyboydov. And there's a related work since last October in 2014 by Alde, BC, and Lukowski for supersymmetric n equal to 4 Yang-Mills theories, which will have some overlap with what I'm going to talk about. So let me begin by summarizing the main results. So most of my talk I will deal with 4-dimensional conformal field theories, and I'll assume that there is a scalar operator with dimension delta phi, and that there is a spin to twist 2 operator, which is usually the stress tensor, and I'll assume that that is the minimal twist operator in the spectrum. And given this, just this minimal information, one can show quite generally, which I'll review in a bit, that there is an infinite sequence of large spin operators of this conformal dimension, which is twice delta phi plus 2n plus L, and plus there is an anomalous piece. L here is the spin of the operator, and n is an integer which tells you that there is an infinite sequence of such operators. Roughly speaking, you can think of n as the twist of the operator, which is the conformal dimension minus the spin. I will focus on 2 interesting limits. One is when the spin is much bigger than this integer n. Loosely speaking, when the spin is much bigger than the twist, and the twist itself is large. And the other limit is going to be when the twist is much bigger than the spin, and spin also is again large. In the first limit, one can show that the anomalous dimension takes on a universal form. There is some number divided by Ct. Ct here is the coefficient that appears in the 2-point function of the stress tensor, times n to the power 4 by spin square. This is universal, first of all, because it does not depend on this delta phi. And besides, given this very minimalistic assumption about the field theory, it will turn out to be true for any conformal field theory. The second limit, which in some sense is more interesting, is when the twist is much bigger than the spin. So if this is much bigger than the spin, you might start wondering if you don't have a large central charge, whether this result can be ever valid, because this will be very big, and because of this sign, it will soon become so negative that the conformal dimension itself becomes negative. So the question that you should ask is, under what circumstance can this be universal, if at all? The other thing that I want you to take note of is that the sign of the anomalous dimension in both cases is negative, and that will play some role in the story that I'm about to say. So if you have a large n in your theory, for some results that I'm going to talk about, you don't really need to think of there being a large n, but probably to be on the safe side, we can think that there is a large n. We can think of these operators as double trace operators of this form. So the spin is the number of symmetrized derivatives that is there. O1 is the operator that you started off with conformal dimension delta phi. The n is the number of times that del square appears. And these double trace operators were pointed out in these nice papers by Heemskerk, Penedonis, Polchinski, and Sully, and also by Scheer and Kyriakos. However, the CFT bootstrap analysis, of course, only yields information about the conformal dimension. It does not tell you anything about what the precise form of these operators will be. And also it will tell you something about the OPE coefficients, and so you should just think of these as schematic form of the operators. So why is this interesting? So as I said, the result is universal. It does not depend on the Lagrangian or the dimension of the seed operator. By the seed operator, I mean the operator that I started off in the 4-point function. It just assumes that there's a twist gap from the minimal twist operator from other operators in the spectrum. And it also turns out that the anomalous dimension of double trace operators is related to bulk Shapiro time delay, and the sign of these anomalous dimensions is related to causality. So there is an interesting interplay between unitarity of the CFT and causality of the bulk, and this was pointed out in a paper last year by Kamano, Edelstein, Maldacena, and Ziboidov. But also, as I will point out, this can be extended to arbitrary dimensions, and so maybe it will have some relevance to the studies of the 3D IZ model at criticality. The other reason why it is interesting is that we'll be able to make some comparison with ADS-CFT with gravity calculations. And there are two different ways of calculating these anomalous dimensions. One of them is the iconal approximation of 2-to-2 scattering. And this was done in a series of nice papers by Cornalba, Costa, Penedones, and Schiappa. And the other calculation is you can think of these anomalous dimensions as arising due to an energy shift in a black hole background. And this was pointed out by Fitzpatrick, Kaplan, and Walters, and we extended this calculation to general twists. So I'm getting cut off on the right. So there's some ultraviolet cutoff naturally on the right. Okay. So it turns out that the results matches exactly with the holographic calculation on the gravity side. Okay. So let me just quickly review Bootstrap so that we are on the same page. So sometimes I'll refer to, so there are two sides to the Bootstrap equation. Sometimes these are referred to as the S channel and the T channel. So you have a 4-point function of 4 identical scalars, and because these are identical scalars in the story that I'm telling you, the exchange operator will be a symmetric traceless object. So it will have even spin. So one of the channels is called the S channel, the other channel is called the T channel. And the Bootstrap equation takes on this form where I've factored out a power of u and taken it to the right-hand side. So on the left, in the S channel, this identity, which was, it can be shown that this in order to reproduce this identity, you need to put in large spin operators on the right-hand side. That's the only way that you can reproduce this identity. The other pieces of the other things that appear in the Bootstrap equation are these OPE coefficient square, which are sometimes conventionally denoted by P. So these are OPE coefficient square, so these are positive numbers. So it was important for in some of the numerical Bootstrap analysis that this was positive. And these are the so-called conformal blocks that David reviewed yesterday. The U and V are the conformal cross ratios, and tau here is the twist, which is the difference between the conformal dimension and the spin. The conformal blocks, closed form expression for the conformal blocks in even dimensions were only recently worked out. So, well, by recent, I mean over the last 15 years, around 15 years back, by Dolan and Osborne. And but there are certain simplifications that occur in certain limits. This formed the premise of these nice papers. In particular, if the spin is large, and if you are in the limit where u is small and v is also small, then it can be shown that the conformal block approximately factorizes. So for some reason, it's getting cut off on the right-hand side. I think it's important that this is rectified, otherwise people won't know what I'm talking about. Can it be done from here, the projector? This is not a part of my time. It's irrelevant.
I'm keeping track of the injury time.
Okay. No, it's getting cut off on the right. Yeah, I think that's better. But it'll, yeah. Yeah, okay. So in this limit, the conformal block, roughly speaking, factorizes, and it has two pieces. One of them, one piece does not depend on the dimension. So this is given by a Gauss hypergeometric function, which does not depend on the dimension that you're working in, and it's a function of only v. So I've displayed this conformal block in one of the channels in the S channel. In order to go to the T channel, you need to interchange u and v. And there's another piece which does depend on the dimension. So in this original work by Fitzpatrick and company, and also by Komargorski and Zibuyedov, this piece was left undetermined because they weren't interested in subleading twist, but I'll be interested in subleading twist, so I'll have to determine, I'll have to tell you what this is. So I think you can maximize it, it's fine. Hopefully we don't have, okay. Yeah. So there are two pieces to the conformal block, one that does not depend on the dimension, the other that depends on the dimension. So anything that arises, any conclusion that you get from this will be true in any dimension, whereas whatever comes from here will be dimension dependent. So it turns out that there are recursion relations for these blocks in any dimension, and the solution to these recursion relations are known only in even dimensions. But in this limit, where you have large spin, and also you have taken u much smaller than 1 and v is less than 1, this recursion relation simplifies and takes on this compact expression. This can be found in this paper by Fitzpatrick and company. But the question is, what solves these recursion relations? So this is something that we were able to guess. It turns out that this fd as a function of v is also given by a Gauss hypergeometric function, which is d-dependent. And we can use this to get some nice analytic expressions in arbitrary dimensions. So the Bootstrap equation demands that leading order, that 1 is reproduced by a function of this form. So there's some function of u, there's some function of v, and it turns out that in order to reproduce 1 from the S channel, you require to incorporate a large spin operators, and you need to integrate over them. So it was shown that in order to match powers of v, we must have the twist given by twice delta phi plus twice n. This is still reviewing old result. These twists are the same as the what happens in MFT or mean field theory, and the OP coefficients are known. We can go to subleading order to determine these anomalous dimensions. The OP coefficients get corrected. The conformal dimension also gets corrected. Now, it turns out that in higher dimensions greater than 2, this anomalous dimension falls off like some inverse power of the spin. And as a result, you really don't require to have a large n to do perturbation theory. The 1 over L actually plays a proxy of an expansion parameter. So that is why I said that sometimes I will not explicitly need a large n in order to talk about some of the results. And our objective is to determine the independence for the anomalous dimension. So just to tell you that we are not experimenters in the sight of in the definition of Sasha Zibuyedov. So we are really doing something analytic. If you look at the Bootstrap equation, after some you really have to you'll get a recursion relation for the anomalous dimension, and it turns out that you can actually invert the recursion relation, and you'll get an equation for the anomalous dimension which takes on this form. So it's the anomalous dimension times spin to the power of the twist of the exchange operator in the S channel. The C's and B's look a bit ugly. These symbols here are what I call the Pochhammer symbols. There are some ratios of gamma functions. And this is a nested sum. This B here depends on this 3f2 hypergeometric function. And this is as far as you can reach in using Mathematica. Okay? But progress is possible. You can do this sum explicitly if you rely on pen and paper. And it's possible to make progress in even dimensions. I will tell you how to do these sums in 4 dimensions. So first of all, this 3f2 can be written in a compact form. And this is just using the basic definition of hypergeometric functions. and as a result of which you reduce your problem to one sum. So your gamma L square takes on this form. I've assumed that the minimum twist operator is a stress tensor, that's why it's L square. So it's you still have to do this particular sum. There is delta phi, you have to do the sum over M. Now you have to do some tricks. You have to use the reflection identity. Then you have to sum over pieces of that expression. Use the fact that the gamma function can be written as an integral. So finally, effectively, the problem boils down to doing a double integral. And this can be done by any entering PhD student. These are the kind of problems that we frequently ask in the entrance interviews. And the answer is in a compact expression. So the sum has been done, and when the exchange operator is a stress tensor, the anomalous dimension takes on this compact expression. So it depends on delta phi. I've arranged it in a power of n. So there is n to the 4, n cubed, n square, n, and n to the power 0. So what do you do with this? So you can ask, what is the sign of this anomalous dimension? It turns out that this is negative and monotonically decreasing with n for any conformal dimension satisfying the unitarity bound. So these are scalars. Scalars have a unitarity bound. It should be greater than or equal to d minus 2 by 2. So for example, if you plot a graph of the anomalous dimension as a function of delta phi, then for n equal to 2 and n equal to 1, it will turn out that the anomalous dimension can be positive. But then this happens only when you violate the unitarity bound. The unitarity bound for d equal to 4 is here. So for any value of delta phi that satisfies the unitarity bound, it is steadfastly negative. So the conclusion here that we reach is that if the unitarity bound is violated, the anomalous dimensions can be positive, but it will be negative otherwise. So let me quickly comment on the general dimensions. You can do similar analysis in general dimension, and you'll get some d-dependent expressions. And to cut a long story short, if your minimal twist is for the exchange on the S channel is the stress tensor, then you get a bunch of expressions which match exactly with the ADS iconal calculation that was done. So also you can plot the anomalous dimension for various values of delta phi as a function of n, and as you can see that they all coalesce for large values of n, which is exactly what our formulas is predicting. In arbitrary dimensions, so this is for d equal to 3, 4, 5, 6, the same pattern continues. So if n is less than d minus 1, then this anomalous dimension can change sign if you are below the unitarity bound, but it is negative otherwise. But you can do better than this. You can actually calculate the subleading terms. I was talking only about the leading term in the anomalous dimension. So the leading term went like 1 over L to the power the twist, minimal twist. You can calculate the subleading term in the exchange as well. So the logic here is that when you plug in this form of the anomalous dimension and you carry out the integrals, then you'll start getting certain powers in the T channel which are not there in the S channel. So these have to vanish on their own. And this gives a nice universal form for the subleading correction as well, which takes on this form. So this is in 4 dimensions. So actually this should have been 2 because I've already put in 2 here, which tells us that the minimal twist is a stress tensor. And you can, in principle, do this order by order, although it becomes quite hard soon enough. But let me just briefly focus on what happens in the other interesting limit, which is when the twist is much bigger than the spin. Now, in this limit, it turns out that it is useful to make a change of variables in terms of h and h bar. So h is roughly speaking n plus L, and h bar is roughly speaking n, because I'm going to be in this limit where n is much bigger than 1. And then you can analyze the Bootstrap equation using saddle point methods, and also using the information that the subleading correction took on that form. And you can argue that the anomalous dimension will take on this nice compact form with certain powers of n and L plus n. And this result actually agrees exactly with the results that were derived by Conformal and company earlier on. So why is this interesting? It's interesting because the formula that I've written here is for general spin and general twist. And in this particular limit, the anomalous dimension for a general spin, general twist takes on a simple form. It does not depend on the twist, it just depends on the spin. So in particular, if Lm was 2, then we'd get n cubed by L. If Lm or the minimum spin of the operator that was getting exchanged in the S channel was 0, then it would go like 1 over n times L, and so on. But the important point is that for higher spins, this is a positive power. So suppose we started off with by assuming that the minimal twist exchange is a stress tensor, then in this limit n much bigger than L much bigger than 1, the anomalous dimension would take on this form. So this is the form that I displayed earlier. This comes from the CT. I've assumed that CT goes like n squared. There will be important corrections. So this would be if there is a massive spin 2 object in the which is not the stress tensor in the spectrum. These would be for higher spin exchanges and so on. The important point is that all of these come with bigger and bigger powers of n. So the question now becomes that suppose you wanted this expression to be valid for any little n. Is it possible? And the answer, of course, in the schematic form is that it appears that it is not going to be possible by just retaining a few extra states on the left-hand side, but rather you will need to, it appears that you will need to take into account all the spins, all the higher spin objects. So this delta that I've written here is some unknown OP coefficient, some unknown thing that tells us that the OP coefficient for the higher spin exchanges falls off in a certain way. You can think of this as being related to some gap in the spectrum. So this will be the leading order correction only if all these terms are much smaller than this leading correction. And that will happen only if little n is smaller than something. It will obviously not happen if you allowed little n to take on any value that you any value. So it appears that to allow for perturbative unitarity, we may need to add an infinite set of higher spin modes for this result to be valid. So this is similar to the conclusion in spirit to the conclusions reached by Kamano, Edelstein, Malderson, and Zeboydov. Of course, in their calculation, they had clever arguments where they were able to conclude that even when n is large, you'll have such a problem with causality. So it will be very interesting to see what a consistent CFT spectrum is, which can lead to perturbatively small anomalous dimensions in a theory with large n and a gap. So let me quickly skim over the holographic side of the story. Fitzpatrick, Kaplan, and Walters suggested a simple calculation. They suggested that the double trace operators can be thought of as two massive particles in ADS rotating around each other. The anomalous dimension arises due to the interacting energy of these particles. So in some sense, you can think of this as a perturbation theory in inverse distance corresponding to Newtonian approximation in ADS. And they did the calculation for n equal to 0. And the result of the calculation agreed with the Bootstrap prediction. Now this is different in spirit to the Eikonol limit where both spin and n needed to be large. So to extend this calculation to non-zero n, little n is quite hard, but we managed to make some progress in the limit where little n itself is big. And it turns out to give exactly the same universal behavior, the functional dependence as well as also all the explicit coefficients, they exactly agreed with the Bootstrap result. So let me just quickly flash this slide so you can do a little bit better. You can put in some alpha prime corrections or higher derivative corrections to see what the role of these corrections is. So when you put in a generic alpha prime correction, there are two things that happens. One of them is they correct the sort of centrifugal potential, so to speak, but they also correct the kinetic term. And it can be shown that the spin dependence for the which went like 1 over L square, if you put in a higher derivative correction, so if you put in an alpha prime to the H correction, it'll get corrected by a term which goes like 1 over L to the power 2H plus 2. Thus it appears that there is no Tuft coupling dependence up to 1 over L to the power 8. So by Tuft coupling dependence, I mean if you did an explicit calculation, then you see the Tuft coupling appearing as a relative coefficient at 1 over L to the 8. So as I said, in this limit, the result agrees exactly with the CFT calculation, and it will be interesting to do the other limit where the twist is much bigger to verify this prediction that we have from Bootstrap that the result is no longer universal. The high derivative corrections will change the result. So summary, we have derived certain interesting universal results using conformal Bootstrap. We should understand the large twist limit better, both from the CFT side and from the gravity side, to understand what a consistent spectrum is. So I'll stop there. Thank you for listening.
Thank you very much. We take a couple of questions.
In the L larger than n limit, you had a bunch of subleading terms.
Yeah.
Sorry. At what point does that approximation? At what point do you start getting something non-universal? Because it seems like you don't have any dependence on the OP coefficients there.
Yeah.
And at some point, I expect there must be dependence on the OP coefficient. So, are you? Is it because you've truncated the conformal blocks in some limit that you somehow can expand out, and you should get some additional corrections if you put in the full conformal blocks, or?
Yeah, so you mean the corrections to the OP coefficient themselves?
No, corrections from the OP I mean, the terms you wrote down are completely universal, but at some point I would expect some dependence on the actual conformal field theory, where you need some additional data besides just the dimensions. You also need the So would you, where does that, what breaks down, I mean, when does that approximation break down?
So to get the leading order correction, we did not really have to work very hard because there are these fractional powers which don't show up in one of the sides. So we just need the fractional powers to cancel off themselves. But then when you go to the next order, it is at that order that you start seeing these other effects creeping in.
Oh, so because I thought you wrote down something universal. You said you could compute many subleading terms, but
yeah. So the statement about universality was about the leading term.
I see. Okay.
Which was important to get actually this closed form expression in terms of L and L plus 2n in the denominator.
Okay.
I think it's related to the question that has been just asked. So what I'm confused about is suppose that the operator that delta phi is a protected operator, so it has some fixed dimension, which is an integer probably. So what's the expansion parameter of this anomalous dimension that you get?
So these are the OP coefficients of not O, but the double trace operators made of O. So this is
sure. The operator is, but the anomalous dimension seems to be independent of any coupling. So what?
No, it's there is a CT in the anomalous dimension. So in the
but CT is the central charge of
in the conformal field theory, yes.
But it's not the cap. I mean, it's not lambda. It's
there is no. Yeah, so you're asking where is the lambda, the two coupling dependence? Yes. So in this particular limit, the leading correction just depends on CT, and the Tooth coupling dependence from the holographic side, at least it seems like it will appear at a subleading order, not at the leading order. So it will go like 1 over L square.
But you mean that in a free theory that would be the same? I mean, so if I take lambda to 0.
Yeah.
So this object would have anomalous dimension
in a free theory.
In a free theory, so lambda equal to 0.
No, but there is we are assuming that there's an expansion parameter which is 1 over CT, right? So
CT is not. Say take n equal 4, it's n square. I mean, it's a number. It's not lambda.
Yeah. So sorry, you're asking.
How can I get anomalous dimension in a free theory?
Okay, so one thing is that in a free theory, so the way that we have set up the calculation, we won't be able to address a free theory question. Because if you want to do the calculation in the free theory, you have to do it the way that Ziboydo was talking about yesterday. That is, I did not explain that in what we set up, there's an approximation that the twist gap between the minimal twist and the next one, delta tau m times log s is much bigger than 1.
Oh, I see.
So there's an assumption there. Okay. So if you wanted to analyze the free theory, you have to do it in the other approximation that Ziboydo was talking about yesterday.
Thank you.
I think due to the time limitations, we have